Hey, welcome back to chemistry. And so now what I want to do is talk a little bit more about the odd behavior of electrons in atoms. So this is more on the development of quantum theory that describes atomic structure, and in particular the motions of electrons in atoms. And so now what we're going to do is describe something called the Heisenberg uncertainty principle. So here we go. So now here's where things were getting a little bit weird. So you might recall in an earlier presentation I was kind of mentioning the fact that electrons can actually be in two different places at the same time in an atom. Now I know that's very hard to believe. This is actually predicted by the pretty advanced mathematics that you use in quantum mechanics to describe electron behavior, but that is really the major implication, is that electrons can be found in more than one place at the same time. And so yes, this would apply for a single electron. One thing we're going to learn about now is that the mathematics of quantum mechanics predicts that even though you can find the electron in multiple places in the atom at the same time, there's really kind of a limited range. And so this range is defined by something called Heisenberg's uncertainty principle. Now here's sort of weird fact number two. So not only can you have electron occupy multiple places at the same time, it can have different speeds or velocities at the same time. So in other words, you can have the same electron going at 5 times 10 to the 6 meters per second, but it also may be going at 6 times 10 to the 6 meters per second. And so it can occupy these two different speeds or states at the same time, which sounds, I know, pretty unbelievable. But what the Heisenberg uncertainty principle will show you is that even though the electron can occupy different speeds at the same time, there's really sort of a range of speeds that can be predicted to be occupied by the electron when it's in the atom. So this is pretty hard to accept. And so there was a scientist that came along later in the 1930s named Schrödinger. And he had a lot of trouble accepting this idea as well. So he had this kind of fun analogy, which I'm going to describe to you, which it helps us understand that we cannot totally deeply understand electron behavior at the atomic level, is because it's stuff that we have never seen before in our macroscopic existence. So let me tell you what this analogy is about. It's called Schrödinger's cat. And so what Schrödinger suggested is, let's say you have just a regular sized cat. So there he is. And so let's say you put this cat into a box. And so there's the cat happily meowing away, unaware of the treachery that is about to befall it, because you are the dastardly scientist. And what you're going to do is you're going to put some radioactivity in the box along with the cat. And you know for a fact that there's a 50% chance that the cat will die within an hour once it's in that box. Okay, so you wait an hour, and so you know that when you open the box, you will pull out either a live cat or a dead cat. And there's a 50% chance of doing each. But importantly, you also know, just from common everyday experience, is that before you open up the box, if you pull out a dead cat, before you open up the box, the cat was dead inside the box before you pulled it out. Same thing with the live cat. If you pull out a live cat, that the cat was most certainly alive in the box before you pulled it out. But here's the thing. This is not how electrons behave. Now let's pretend that now our cat is the size of an electron. What would the cat be like in the box before you pulled it out? Well, it wouldn't either be alive or dead. Instead, it would be alive and dead at the same time. It would occupy these two same states at exactly the same time. It would be sort of a mixture of liveness and deadness. Now, I know that sounds very difficult to believe, but this is the prediction for quantum mechanics for very small objects, in that they can occupy multiple places or multiple speeds at the same time. However, if you were to pull this cat, the size of electron, out of the box, even though it's kind of in this mixture of live and dead within the box, but as soon as you pull it out of the box, it becomes either live or dead. So the actual act of measurement of a cat the size of an electron forces it into a final state of either being alive or dead. But importantly, what this principle says is that applied to electron, it can be at multiple states at the same time. It can have multiple speeds at the same time or multiple velocities at the same time. So this brings us to the Heisenberg uncertainty principle. And so now you understand electrons can be in a range of places at the same time, and they can also have a range of velocities at the same time. So what the Heisenberg uncertainty principle says is that the range of velocities, which is symbolized by delta V, that electrons can occupy is inversely related to the range of positions, which is delta X it can occupy in an atom. So we have an equation there, which is the Heisenberg uncertainty principle. And what you can see is that delta X, the range of positions, multiplied by the mass of whatever you're considering, usually an electron, times the range of velocities must be greater than or equal to that constant there. That's h, which is Planck's constant, divided by 4 times pi. So let's look at this equation a little bit more carefully. So you can see that delta x times mass times delta v must be equal to or greater than a constant, which is some arbitrary number. Now, what I'm hoping you can see is that if you look on the left side of the equation, imagine that you were to, for some reason, increase the value of delta x, meaning you were to increase the ranges in which you could find electrons in atoms. If you were to do that, in order that number to remain a constant, you would have to correspondingly decrease the range of velocities. So as the range of possible positions an electron or other small object can occupy increases, the range of velocities that electron must occupy decreases. So they're inversely related to one another. And again, the reason why that happens is just to make sure that the total range of velocities times the range of positions times mass is going to be above a certain constant. Another way you can restate this equation, and which is often spoken of this way, is one of the things you'll learn in physics is if you take mass of an object times its velocity, it's called momentum. So another way you can restate the equation is just substituting momentum, which is symbolized by P, for m times v. But if it's m times delta v, it would be delta p now. So we're now a change of momentum. So another way of saying Heisenberg uncertainty principle is that the range of positions, x, times the range of momentums, p, has to be equal to or above that constant. What the law basically says is this, is if you have a very narrow range of positions that the electron will occupy in an atom at the same time, there must be a correspondingly very broad range of velocities that the electron will have in that atom at the same time. In other words, if delta x is relatively small, delta v is relatively large. But it can go the opposite direction. If there's a very broad range of positions that the single electron will have at the same time, there will be a relatively narrow range of velocities it will have. In other words, if delta x now is very large, delta v will be really small. So what I want to do now is do some problems using this equation. So let's go through the equation in detail. So there, delta x is the uncertainty position, and the units usually used are meters. Now, when you see that delta sign there, usually we think of delta as change, but in this time, delta means range. It's a range of values that it could have. And I think that'll become more understandable when we do a problem. And then we have mass, which will be measured in kilograms. And then we have the range of velocities that that thing can occupy. And that will be the uncertainty of velocity. So that will be in meters per second. And then it's going to be greater than or equal to that constant h divided by 4 pi. So that equal sign there in the equation should be a greater than and equals to sign. Okay. And so h is Planck's constant, which you already know about. One thing that is kind of helpful to remember is that you're going to be having joules probably in this equation. And so keep in mind that joules can be converted to kilograms, meters squared per second squared. And again, just to mention again, when you see the delta sign, this time it means the range of positions or velocities, or another word is uncertainty of positions or velocities. So let's go ahead and try this problem. So it says an electron in an atom has a mass of 9.11 times 10⁻31 kilograms and moves at an average velocity of 5 times 10⁶ meters per second. let's say an experiment measures this velocity, and we know at the same time that the uncertainty or range of the velocity in this measurement is 1% of this value. Calculate the uncertainty of position of the electron and compare this to the size of the atom. Okay, so I want to go ahead and try this problem out. So let's get some facts onto the board here. So we have a mass of an electron, which is m, and it's going to be 9.11 times 10 to the negative 31 kilograms. So that will be the mass of an electron. So I think we're also given, it looks like, a velocity of the electron. So velocity is, I guess, 5 times 10 to the 6 meters per second. And so we can maybe from this information figure out what the range or uncertainty of the velocity is, and then use Heisenberg's uncertainty principle, that equation which I just showed you, to find the range of positions that this electron will be. So in the end, what we're trying to find is delta x, the range or uncertainty of positions that the electron will have in this atom. And so what you would have to do is from this velocity, from the problem, figure out what the range of velocities you would have for this electron. And if we can figure that out, then we can plug it into Heisenberg's uncertainty principle and figure out the range of positions the electron will have in the atom. So let's look at what the Heisenberg uncertainty principle is. And so it is going to be, so it's going to be the delta x, the range or uncertainty of position, times the mass times the range or uncertainty of velocity that this object will have, in this case an electron, is going to be equal to a constant number, actually greater than or equal to a constant number, which is going to be h over 4 pi. Okay, so what you can see is in order to use this formula, you need position as a range of positions, but you need velocity as well as a range of velocities. In other words, you cannot plug in v into this equation. You have to convert v to delta v, and then you can plug it into the equation. So do we have some information that tells us, given the velocity, what would be the range of velocities that the electron can occupy given this technique to study the electron? And so we are told there in this problem that the uncertainty of the velocity measurement is 1% of the value of the velocity. So to figure out delta v, we have to take 1% of this value of the velocity. So it's going to be 5 times 10 to the 6 meters per second. And we're going to be multiplying it by the uncertainty, and it's going to be in decimal form, so it's 1%, it's 0.01. So delta v should be 5 times 10 to the 4 meters per second. So this is a delta v that we can enter into the equation. So let me go ahead and plug in some numbers and see what this works out to be. But first, let me go ahead and solve this for the uncertainty position delta x. And so it's going to be delta x, I'll write this down here, delta x is going to be equal to h divided by 4 times pi, and then mass times delta v goes into the denominator, times mass times the change in velocity. And so that should give us what the range of positions would be. So we plug in some numbers here. H is equal to 6.626 times 10 to the negative 34. So normally with Planck's constant I would write joules per second, but because I have a mass here in kilograms, let me just convert the joules per second into kilograms meters squared over second squared times second. So let me just do that now. So it's kilograms meters squared over second squared times second, because kilograms meters squared per second squared is a joule, and then Planck's constant is joules per second. And then in the denominator we have 4 times pi, which is 3.14159. Mass is that number there, 9.11 times 10 to the negative 31 kilograms. And then delta v, so again, we don't want the velocity here, we want the change in velocity, which is going to be 5 times 10 to the 4 meters per second. Okay, so anyway, you can work out the math. And so that answer there on the screen should be correct. See if I can read it there. Yeah, so it's 1.16 times 10 to the negative 9 meters. So this is the range of a position, x. Oops, sorry about that. Range of a position that an electron can occupy. All the places where the electron can be at the same time can occupy in an atom given this range of velocity. So the range of velocity is, when using this technique to measure velocity, is pretty accurate in the sense that the uncertainty is relatively low. So it's about 1% uncertainty. So let's kind of evaluate what this range or uncertainty of position of the electron in an atom is. So as I just kind of mentioned, atoms are very small, and so they're typically 0.1 to 0.3 times 10 to the negative 9 meters in size. And so I think here in this problem, I think we have what, 2 times 10 to the negative 10 meters, which is going to be 0.2 times 10 to the negative 9 meters. So here we have an atom here, and so the width of the atom here is 0.2 times 10 to the negative 9 meters, yet the range of positions where the electron can be at the same time is 5 times the value of the width of the atom. It's approximately 1 times 10 to the negative 9 meters. So basically what Heisenberg's uncertainty principle is saying in this problem, when you're dealing with the realm of very small objects like atoms, if you have some kind of technique where you can get a relatively accurate measurement of the range of velocities that the electron can be in, you're not going to get a very accurate measurement of the range of positions that the electron can be in at the same time. It's going to be much broader than the size of the atom, so it's basically useless. So this is, again, another reaffirmation that you really cannot, with very small objects, get an accurate measurement of the velocity and the position at the same time. If you have an accurate measurement of the velocity, which you did in this problem, you would not get an accurate measurement of the position, and vice versa. Okay, so let's move on. Okay, so now, believe it or not, you can use this uncertainty principle for everyday objects like baseballs. So let's just apply the uncertainty principle to a baseball and see what the results might tell us. And so we have a baseball here, and the same uncertainty principle would apply, that the uncertainty of any measurement of its position, delta x, is going to be multiplied by the mass of the baseball times the uncertainty of any velocity that you can measure with the baseball, and it's going to be a number greater than or equal to h over 4 pi, which is a constant. Okay. So let's kind of see what the answer would be with an assumption that we, say, have a pitcher throwing an 80-mile-per-hour baseball, and let's say we have a device like a radar gun that can measure the baseball at 0.1 miles per hour. So that's relatively accurate measurement of the baseball's velocity. That's pretty good. So let's go ahead and take those numbers. We have a mass of the baseball, which is 0.145 kilograms, and we have an uncertainty of the baseball speed, which is going to be 0.1 miles per hour. And so you can take the uncertainty of the baseball speed, which is 0.1 miles per hour, which is about 0.045 meters per second. And then what you can do is you can multiply it by the mass of the baseball, and what you'll get for a term m delta v is that number there, which is 0.0065 kilograms meters per second. So from this information at this point, given that we have a 0.1 mile per hour uncertainty in the velocity of the baseball, let's say is going about 80 miles per hour, let's go ahead and calculate what the uncertainty of the measured position would be. Well, if you went ahead and did that, what you would discover, the uncertainty of the position of that baseball is going to be very, very small. But the laws of quantum mechanics do apply to everyday objects like baseballs. And so it predicts that, yes, if you have a baseball going at a certain speed, it will have a range of velocities it can be found in at the same time, and a range of positions in space that can be found at the same time. But even if your device is very, very accurate at measuring the range of the velocities which that baseball can be in, what you'll get is a number for the range of positions that is very, very, very small, which is 8.1 times 10 to the negative 33 meters. And so the range of positions you just simply could not measure with any kind of device. Even though the Heisenberg uncertainty principle predicts that the baseball is going to be in multiple places at the same time as it's heading toward you, for all intents and purposes, we can just assume that it's really only going to be one place, because you could not, with any instrument, figure out how close those baseballs are going to be to one another, because that distance between the baseballs in that range of places is very, very small, times 10 to the negative 33 meters. So here I have some consequences of the Heisenberg uncertainty principle. And what you can see is that what we just saw with this previous problem, when we're dealing with baseballs, the laws of quantum mechanics, including the Heisenberg uncertainty principle, does apply to baseballs, but it really suggests that, sure, that the baseball can be found in multiple places at the same time or multiple speeds at the same time, but those places and speeds are extremely close to one another that you could really never be able to see the difference in that range. And so for all intents and purposes, we can describe the motion of objects like baseballs or larger objects like planets with the classical laws of motion, like force is equal to mass times acceleration. However, if you're at the level of the atom, at the level of the very small, where the mass of the atom is tiny, then what you can clearly see with the previous problem is that you really cannot determine accurately for an electron its position or its velocity at the same time. So we can never really truly plot any kind of accurate trajectory of the electron's motion in the atom. Instead, all we can do is we have some idea approximately where the electron can be found given certain circumstances. And so we'll know from, for example, if you have an atom and you have a nucleus and you're going out a certain distance in space, we will know what the probability of finding that electron is, but we won't know for certain exactly where on that distance it will be. The places in space where you are most likely to find the electron away from the nucleus, those places in three-dimensional space are called not orbits, but orbitals. So now what we can see is, based on some of the things we've talked about with quantum mechanics, that we need a new model of an atom. So the model that we kind of talked about previously, which is the Bohr model, where electrons travel in defined trajectories in orbits around the nucleus of the atom. Although that model is pretty good about predicting for hydrogen where the wavelengths of the emission spectra will be, it really cannot be used for much of anything else. So for example, you can't even use Bohr model to predict the emission wavelengths for other atoms like lithium or sodium or anything like that. So the Bohr model is pretty limited in its use. So in 1928, in realization of laws of quantum mechanics that were being developed, a new model of the atom was created, the quantum mechanical model. It's also called the wave mechanical model of the atom. And so this was created by three men, Erwin Schrödinger in Germany, Werner Heisenberg in Germany, and Paul Dirac in England. All three got Nobel Prizes for their work. So this new model, the quantum mechanical model of the atom, was based on three ideas which I just kind of mentioned. That electrons, not only are they particles, but they also have a wave nature. And you might remember we used the de Broglie wave equation to understand to some degree where we can find electrons in the atom, how far away from the nucleus they are. Another thing that this new model of the atom uses is that Heisenberg uncertainty principle. Again, it's the idea that you really cannot determine accurately the velocity and the position of an electron at the same time. Another thing that is applied in this new model is one of Bohr's ideas was correct. Although you cannot describe electrons as going in orbits around the nucleus, Bohr suggested that in those positions at distances away from the nucleus, those electrons have certain energies, and that those energies are defined numbers. And so those energies are said to be quantized. And so putting this all together, what it basically says again is that when you have an atom, you're looking at electrons. we'll never know exactly where the electron is because we cannot define a trajectory for it. But we have some idea of the probability of how far away the electron will be from the nucleus. Now, there are equations that describe how far away from the nucleus these electrons will be found, and these are called wave equations or wave functions. And so the main equation that is used to describe where the electrons are truly found in the atom and generally how far away they are from the nucleus is called the Schrödinger equation. It's also called the wave equation. The reason why it's called the wave equation is due to Broglie's idea that when you have standing waves at a certain distance from the nucleus, only ones at a particular distance away will constructively interfere with one another, and you'll get a good standing wave that reinforces itself. And so it's at that relative position that you might be able to find an electron. Now, you can go a little bit maybe further out, and you can create other standing waves where you can find electrons. And so these standing waves are modeled using this wave equation, the Schrödinger wave equation. The only thing you really need to understand about that is that these standing waves basically tell you the regions in space where you're most likely to find an electron, where you have a high probability of finding an electron, and those regions in three-dimensional space are called orbitals. And one of the things we'll be talking about next is when you have this Schrödinger equation, which tells you all the orbitals that can exist around the atom, which define where the electrons are in the atom, these particular orbitals are defined by constants. These constants, there are three of them, they're called quantum numbers. And the quantum numbers are constants which are applied to the Schrödinger equation, which kind of map out the orbitals in space. So we will learn about these quantum numbers in the next lesson.